Hello friends, this is Dr. Manimozhi from PG and Research Department of Physics. In this video, we are going to discuss about Ruby laser. In this video content, we are going to discuss a short introduction on Ruby laser, properties of laser, basic concepts of lasing action, Ruby laser construction and working, energy level diagrams, applications, drawbacks, and some historical importance. What is laser? LASER is an acronym of Light Amplification by Stimulated Emission of Radiation. It is a device which produces a coherent beam of optical radiation by stimulating electronic, ionic or molecular transition to higher energy levels. Mainly used in single mode systems, light emission range will be from 5 to 10 degrees and it requires higher complex driver circuitry than LEDs, and laser action occurs from three main processes that we'll be discussing in the upcoming slides. Laser light has very specific properties. Most important of them are listed here. It is monochromatic, having only one wavelength. It is highly coherent, that is, all the emitted photons bear a constant phase relationship with each other in both time and phase. And it is highly directional, a very tight beam which is very strong and concentrated. There are some main components one should know to understand lasing action. They are absorption, spontaneous emission, stimulated emission, and population inversion. Energy is absorbed by an atom. The electrons are excited into vacant energy shells. This is called as absorption. Here you can see the diagram. E1 is the ground state energy level and E2 is the excited state energy level. The atom absorbs energy h nu and it is excited to the higher energy level E2. After excitation, the excited atoms from the higher energy states decay to lower energy state by emission of photon of energy E is equal to h nu. This is called as emission and it is a random process. The stimulated photons have unique properties. They are in phase with the instant photon. They have the same wavelength as the instant photon and also travel in same direction as instant photon. The important condition for laser operation is the condition of population inversion, where there are more number of atoms in the excited state than in the lower energy state. When this occurs, stimulated emission prevails and light gets amplified. Population inversion is produced by pumping. There are different types of pumping depending upon the sources, like optical pumping, which is done by photons, electrical pumping by electrical discharge, etc. A ruby laser is a solid-state laser that uses a synthetic ruby crystal as its gain medium or lasing medium. It was the first type of laser invented and was first operated by Theodore H. Ted Meeman at Hughes Research Laboratories in 1960. The ruby mineral is aluminum oxide with a small amount for about 0.05% of chromium, which gives its characteristics pink or red color by absorbing green and blue light. The ruby laser is used as pulsed laser producing red light at 694.3 nanometer. After receiving a pumping flash from the flash tube, the laser light emerges from as long as the excited atoms persist in the ruby rod, which is typically about a millisecond. In a ruby laser, we use flash tubes as energy source or pumping source. The flash tube supplies energy to the laser medium, that is to the ruby. When low energy state electrons in the laser medium gain sufficient energy from the flash tube, they jump into the higher energy state or excited state. The ends of the cylindrical ruby rod are flat and parallel. The cylindrical ruby rod is placed between two mirrors. The optical coating is applied to both the mirrors. The process of depositing thin layers of metals on glass substrates to make mirror surface is called silvering. Each mirror is coated or silvered differently. At one end of the rod, the mirror is fully silvered, whereas at another end, the mirror is partially silvered. The fully silvered mirror will completely reflect the light, whereas the partially silvered mirror will reflect most part of the light but allows a small portion of the light through it to produce output laser light. You can see all the things in the figure. The rod's end has to be polished with great precision. such that the ends of the rod are flat to within a quarter of a wavelength of the output light and parallel to each other within a few seconds of arc. The rod with its reflective ends then acts as a Fabry-Perot echelon. Here are some important lasing action steps. First one is absorption, then metastable state, spontaneous emission, stimulated emission and amplification. In absorption, chromium ions absorb energy from the flash lamp and move to the excited state. In metastable state, excited ions transition to a long-lived metastable state. Spontaneous emission, ions drop to the ground state releasing photons. And in stimulated emission, photons stimulate other excited ions to emit more coherent light. And amplification, light reflects between mirrors amplifying intensity. We assume that the energy levels will be E1, which is less than E2 and E3. So E1 is the ground state energy level and E2 and E3 are excited state energy levels. The energy level E1 is known as ground state or lower energy state. The energy level E2 is known as metastable state and energy level E3 is known as pump state. Let us assume that initially most of the electrons are in the lower energy state E1 and only a tiny number of electrons are in the excited states E2 and E3. When light energy is supplied to the laser medium, that is to the ruby crystal, the electrons in the lower energy state or the ground state E1 gains enough energy and jumps into the pump state E3. The lifetime of pump state E3 is very small, that is 10 to the power of minus 8 seconds. So the electrons in the pump states do not stay for a long period. After a short period, they fall into the metastable state E2 by releasing radiationless energy. The lifetime of metastable state E2 is 10 power minus 3 seconds, which is much greater than the lifetime of pump state E3. Therefore, the electrons reach E2 much faster than they leave E2. This results in an increase in number of electrons in the metastable state E2 and hence the condition of population inversion is achieved. After some period, the electrons in the metastable state E2 falls into the lower energy state E1 by releasing energy in the form of photons. This is called as spontaneous emission of radiation. When the emitted photon interacts with the electron in the metastable state, it forcefully makes the electron fall into the ground state E1. As a result, two photons are emitted. This is called stimulated emission of radiation. Coming to the applications of ruby lasers have declined in use with the discovery of better lasing media, but still they are used in number of applications where short pulses of red light are required. Holographers around the world produce holographic portraits with ruby lasers in sizes up to a meter square. Many non-destructive testing labs use ruby lasers to create holograms of large objects such as aircraft tires to look for weakness in the lining. Ruby lasers are used extensively in tattoo and hair removal. There are certain drawbacks of ruby laser. The laser requires high pumping power because the laser transition terminates at the ground state and more than half of ground state atoms must be pumped to higher state to achieve population inversion. The efficiency of ruby laser is very low because only green component of the pumping light is used while the rest of the components are left unused. The laser output is not continuous but occurs in the form of pulses of microseconds duration. The defects due to crystalline imperfections are also present in this laser. The historical importance of ruby laser is that the ruby laser was used for the famous laser ranging experiment which was conducted with a corner reflector placed on the moon by the Apollo astronauts. This determined the distance to the moon with an accuracy of about 15 centimeter. So this is the importance of the ruby laser. Thank you.